I would like to talk about the HD plus ion and HD plus spectroscopy, and particularly to speak about the spin orbit term in the hyperfine structure interaction. The reason for that is the following, that, I should say a few words before. We have two authors of this presentation, me and Jean-Philippe Carr from Paris. And here are my collaborators, which contribute to some things which will be presented in my talk. But the reason for my talk, I start again from the first page, is that there were several new experiments in spectroscopy of HD+, where the hyperfine structure resolution for pure rotational transitions, for vibrational transitions, the hyperfine structure has been resolved with very high accuracy, and that one of the theoretical limitations for analysis of experimental measurements and theoretical data was not very accurate calculation of the spin orbit interaction in this case, and in case of HD plus ions. So that is the main reason why I choose this title for my talk and this topic for this case. So I want to start from the NRQED Lagrangian, which we used for our consideration of the spin orbit interaction. I want to say, to draw your attention to this particular paper, an introduction to NRQED by Gil Paz, where he showed that in principle we may build up the NRQED Lagrangian from some building blocks, some operators which are written here, using the symmetries which we have for NRQED, namely spatial parity, time reversal symmetry, gauge invariance, and so on and so forth. And then we may build the Lagrangian using this type of expansion, like here, and using the properties of these operators, rotational symmetry, and so on. And it is very interesting that from this consideration, we can easily show that this Lagrangian is unique, at least when we expand this Lagrangian in terms of inverse masses, and for some particular power of masses, the term would be unique with some arbitrariness, which can be seen from the different choice of basis for homogeneous polynomials, like I wrote here. P is, say, in this case, the impulse operator, which acts either on the front of the operator or at the very end of the operator, in between. With this simple arbitrariness, we can fix the Lagrangian for further consideration. In our case, when we use powers of masses for electron up to m to the fourth, the Lagrangian looks like the one which I wrote here, and the coefficients can be obtained by matching the scattering amplitudes from QED and NRQED. So matching these coefficients, the Wilson coefficients of the Lagrangian, in this case, I wrote the Hamiltonian, not the Lagrangian, but it's very easy to come from one form to another form. The coefficients should be taken as follows, as written here. They are uniquely identified from the scattering amplitudes. Here I have some libertine formulas because here should be the cutoff parameter instead of just log alpha. But for simplicity, I just left log alpha terms, and this will help me to write down the coefficients for the spin-orbit interaction. So having this NRQED Lagrangian up to this term, which should be enough for calculations of the binding corrections up to the order m alpha to the seventh. And with these coefficients written here, so we may calculate different properties, binding properties of the systems under consideration. In our case, we use we have a system with one electron and two heavy particles. The heavy particles, of course, we consider as so relativistic part we consider in the leading order term. So Breit-Pauli, Hamiltonian for their interactions. So now I come to the advanced spin theory. In this case, in case of HD plus molecular ion, the effective Hamiltonian for the hyperfine structure for individual state should be written. Can I change because I do not see some part of my transparencies? Okay. The hyperfine structure effective Hamiltonian has this form. In the leading relativistic approximation, in the Breit-Pauli approximation, there are some other higher order in alpha contributions which may be more complicated, but we will discuss a little bit later about them. What is important in this effective Hamiltonian? The major terms which appear here, which are important, they are proton spin, electron spin interaction, and deuteron spin and electron spin interaction. These two coefficients are the largest in this effective Hamiltonian. The third term is the E1 spin orbit interaction of the electron, which is under consideration in this talk. Sorry. here is the coupling scheme of spins, which is written here. And you see that the largest separation of the hyperfine structure is due to the proton-electron coupling. The next is the neutron-electron coupling, the next splitting. And the remaining part is the interaction with orbital part. In case of spin-orbit interaction, we have the leading order term relativistic correction, which is well known from the Wright-Pauli Hamiltonian, and it is written here. The effective Hamiltonian at m alpha to the 6th order was written in our paper of 2020, and I will show the reference later. But what we got there, this leading or the first order term, which has 4 interactions of this type, and 2 interactions of Seagal type, which are written here. And then there are second order interactions. The sum of them is here, and the particular second order contributions are written here. Here I should say that since we consider also the m alpha to the 7th order contribution, log alpha, we do not consider here the non-logarithmic contributions. So that's why we consider only terms with log alpha at this order. So we need to add to these 3 second order contributions the 4th one, which also contribute something like this type of operator. So we separate this operator with this coefficient CD Darwin term here, and have 2 contributions. One comes to m alpha to the 6th order, and the second one comes to the m alpha to the 7th order, log alpha. And what is important that in this case, both first and second order terms are finite and do not require any regularization or cancellations of infinities and so on. So now I turn to results. For pure rotational transition, from ground state to first vibrational state, in experiment they had 6 lines measured, which are marked here by bold numbers, 1, 2, 3, 4, 5, 6 transitions. And from these 6 measured transitions, in principle, knowing coefficients of the effective Hamiltonian, we may fit the experimental value of the coefficient, and we've got it something like here from this data, from these 6 measurements. And here is the calculation of the E1 coefficient for the first vibrational, rotational level, since for L0, E1 is just 0. There is nothing to calculate in this case. But for first rotational state, we need to calculate this quantity, and the leading order term, which was obtained in our previous considerations some time ago, maybe 10 or more years ago, we got this quantity from the Bright-Pauli leading order approximation. Then we got this value for m alpha to the 6th order correction, and we realized that the log term contribution at order m alpha to the 7th should not be very small. And really what we got here is written here. It is just only 3 times smaller than the m alpha to the 6th order contribution. So it's also very important. And our final value for theoretical E1 coefficient is this one. And what we can see from here that we still have some disagreement with experiment. The error bar which we put here is 1/3 of this contribution. It's rather conservative error estimate which we have in this case. And so I think it is rather trustworthy error bar estimate. So we have some disagreement here. Sorry?
Conclude? Could you please try to conclude?
Yes, sure. I have one more transition and 2 more slides, just only 2 more slides. The other transition is the two-photon vibrational transition. There are 2 transitions from this spin state to this spin state, the one transition, and from this spin state to this spin state, the other transition. They have separation from the spin averaged value. One transition is this value, the other is minus 63 megahertz. So what we have from theory for this transition, we have 2 coefficients E1 for this state and for that state. Similarly, we have contributions from the leading order term, from the Bright-Pauli Hamiltonian, from m alpha to the 6th order, and the log alpha m alpha to the 7th order term. So the total value is this one, and the error bar is similarly as in case of previous transparency. The same is here. So what we got in our case, the separation of the 2 observed transition lines experimentally was obtained, and its value is this one. In case of theory, we have again some discrepancy, and the error bar is here. Again, we use the very conservative estimate of error bar is 1/3 of this contribution, something like that. So we see that in both cases, we have a small disagreement between theory and experiment. What is the reason of this disagreement? I cannot say. But in conclusion, I want to say that what was already done. The spin-spin part, which is the most important in all these considerations for the hyperfine structure, has been calculated by us with the precision, I think, even better than 10 to minus 6. But we put here the estimate something like of order 10 to minus 6. The spin orbit is now known up to m log alpha alpha to the 7th order. The spin-spin tensor contributions also are available now to m alpha to the 6th order. We should state here that there is no log alpha alpha to the 7th order terms for this contribution here. So the uncertainty for these two terms is something like alpha to the 7 or in energy, m alpha to the 7 in energy. Other contributions which come from high order corrections, one of them nuclear spin-spin interaction mediated by the electron spin. We consider in the other previous conference, on FFK fundamental constant conference, which held last fall and is available in this Los Alamos archive paper, and it was shown there that the contribution from this term is much smaller than the discrepancy. So my conclusion that probably the error bars of experiments were underestimated. And that is the last slide, and thank you for your attention and your questions.
It is nice to hear that 10 sigma discrepancy is a small discrepancy.
Oh, well.
Anyway, questions? So let me remind you that HD plus is now the best way to determine the, not the best way, but one of the best way to determine the mass ratio of proton to deuteron. So it is very, we can calculate, Vladimir Korobov can calculate very accurately. So it's up to the uncertainty.
Maybe it's better to say that, okay, maybe it's better to say that we can infer some mass relation between proton and deuteron and electron mass, which can be inferred from a comparison of theory and experiment with very high precision, from which we can extract proton to electron and proton or deuteron to electron mass ratios.
Thank you, Vladimir.